So in this video, what we're looking at are Riemann sums. So let's consider a region bounded by the graph of f of x equals the square root of x, the x-axis, and the lines x equals 0, x equals 1. Okay, we want to find the limit as n approaches infinity of the sum of f of ci delta xi from I equals 1 to I equals n. Now in this case, ci is going to be the right endpoint of the partition, and it's going to be given by ci equals I squared over n squared. So notice this is 1 squared over n squared, this is 2 squared over n squared, 3 squared, all the way to n minus 1 squared over n squared. So delta xi is just the width of that, which we can tell would be x1 minus x0 for this one, x2 minus x1 for this one, x3 minus x2 for this one, right? So we're looking at ci minus ci minus 1, okay? Or delta xi equals I squared over n squared minus I minus 1 squared over n squared. Do y'all see that? How this is ci, this is ci minus 1. Okay, so it's really important that we be able to say that delta xi equals I squared minus I squared minus 2I plus 1 all over n squared. That's going to be 2I minus 1 over n squared. Alright, so it's important that we know what delta xi is. So now, we know we're finding the limit as n approaches infinity of the sum from I equals 1 to n of f of ci delta xi. Now, we know ci is given as I squared over n squared. We know that delta xi is what? 2I minus 1 over n. So we're going to say, okay, so we're talking about f of x, so f of ci is the square root of I squared over n squared, which is just I over n. So we're really just looking for the limit as n approaches infinity of I over n, sum of I over n times 2I minus 1 over n. So we're talking about the limit as n approaches infinity of the sum from I equals 1 to n of 2I squared minus I over n squared, which is the limit as n approaches infinity of 1 over n squared, the sum of 2I squared minus I. Now, we're going to use our summation formulas. This is going to give us, I'm going to leave that limit off, and I'm just going to say that this is equal to 1 over n squared times 2 times the sum of I squared, which is n times n plus 1 times 2n plus 1, all over 6 minus I, which is n times n plus 1 over 2. So we got 1 over n squared times, that's going to give us over 3. So we're going to have n cubed plus, or 2n cubed plus 3n squared plus n over 3 minus n squared plus n over 2. Alright, so this is going to give us hold on, let me make sure I got something right here. Yeah, I missed a square, didn't I? 2I minus, so I hope y'all caught that. So that's n squared, which means this is n cubed, which means that there's an n cubed on the outside. hopefully y'all caught that. If not, how did I know this highest? We know that these should cancel out. So if you ever get something like that, you'll know that you've kind of made a mistake somewhere. So this is going to give us, let's go ahead and multiply this out. So we'll get 2n cubed over 3n cubed plus n squared over n cubed plus n over 3n cubed minus n squared over 2n cubed minus n over 2n cubed. So this is going to give us 2/3, right, the n cubes cancel out, plus 1 over n plus 1 over 3n squared minus 1 over 2n minus 1 over 2n squared. So if I take the limit as n approaches infinity of all of that, well, that goes away, that goes away, that goes away, that goes away, and I equal 2/3. So there is exactly what we're looking for. Now, notice that this example used a partition that did not have equal widths, right? The subintervals were all different width. And now the reason that this particular partition gave the proper area is that because as n gets bigger, the width of the largest subinterval approaches 0. Okay? The key of this feature is This is the key feature of the development of what we're going to call the definite integral. Okay? Now, in the definition of the Riemann sum below, we want to note that the function f has no restriction other than it's defined on the interval from a to b, the closed interval. Okay? So, here's our definition. If we let f be defined on a closed interval from a to b, and let the delta be a partition of that interval from a to b, given by a equals x sub 0, which is less than x sub 1, which is less than x sub 2, all the way down to x is less than n minus 1, which is less than x sub n, which is equal to b. And in this case, delta xi is going to be the width of that ith subinterval. So we're saying it's that this is the ith interval. So we know that delta xi would be xi minus 1. We used that just a second ago. Now, if ci is any point on that ith subinterval, then this sum is called a Riemann sum. Notice that c has to be between the endpoints of that ith subinterval. Now, the upper and lower sums that we did are examples of Riemann sums. They're very specific Riemann sums that have regular subintervals and use either the left endpoint or the right endpoint. These are not necessarily things that we have to have for a Riemann sum. It just makes for a really pretty one. Now, the width of the largest subinterval of a partition delta is called the norm of that partition. It's denoted by these double bars around it. So this is like the magnitude. Remember when we did the magnitude of vectors? This is kind of the magnitude of that length, that delta. That's that length of that partition. And it's the largest length. So if every subinterval has the same width, then that is a regular one, and its norm is denoted by b minus a over n. We've done this. That was the easy ones. Notice what happens. As n goes to infinity, the norm goes to 0. So this is kind of going to be important. Now, for any general partition, the norm is related to the number of subintervals in this following way. So notice that if we took this, we know that delta x is the greatest, right? It is the largest subinterval. So if delta x is the greatest b minus a over n, if I multiply both sides by n, divide by delta x, then I wind up with n has to be greater than or equal to b minus a over the norm. Okay? So this is kind of an important thing too. Now, the number of subintervals in a partition approaches infinity as the norm of the partition approaches 0. What this means is as we're going to say that the norm approaching 0 implies that n is approaching infinity. Now, this is not always true the other direction. I can't say that just because n goes to infinity that the norm will go to 0. Because what if we have this partition here? 1 over 2n. Okay? This is going to give us something that looks like this. Our first one is really close, and we're saying that as n goes to infinity, our smallest one gets really small, but our biggest one is still always going to be 1/2. So this doesn't mean that n going to infinity implies that the norm goes to 0. So, if you have any questions about that, please just shoot me a reminder or ask questions in class.